Okay, this video is going to be for the infinite series unit for calculus. We're going to talk about two things here, alternating series and telescoping series. The alternating series test is an official test. The telescoping series is just a form of series that we can do a procedure on in order to calculate uh, whether or not, or determine whether or not the series converges or diverges. Alternating series test is used very, very frequently. Telescoping series is probably the rarest of all the tests, but they both involve mixtures of positive and negative terms, so it's good to kind of consider them together. All right, so first, what is an alternating series? An alternating series is simply a series whose terms alternate. So usually you can tell that you have an alternating series when you have part of your generator rule has either -1 to the n or -1 to the n plus 1 or -1 to the n minus 1. Because as you go up in n, these alternate from positives to negatives. So you end up with a positive term, a negative term, a positive term, negative term, positive term. So that's all that's meant by an alternating series is the sign of the terms is alternating from term to term, specifically that way. Right, so the alternating series test is useful to determine whether an alternating series converges, but it cannot be used to determine that the series diverges. So this one is only used to determine that a series converges. All right, and what we say is if you have an alternating series and you have positive terms, so in other words, a generating rule that generates some terms, although technically I guess it could be negative, because this will change the sign. You have to have an alternating series, specifically that, right? Then it will converge if the following things can be shown to be true. The limit of the generating rule ignoring the signs is 0, and secondly, that the series is decreasing. So this means, well, really, I'm going to call it decreasing. Technically, it's non-increasing. Right? So you have to have a series whose terms never go up. They can either be equal to each other or they can go down. So the next term is lower than the current term. Okay? And there's a couple ways to show that. Sometimes you can just, like we were doing for direct comparison, show that the rules for the next term and the current term are in such a way that because of the way fractions behave, that's true. Or you can use a derivative to show that this is true if it's more complicated. Okay, so we'll take just a couple of examples here. So this is pretty short, but I think it's pretty easy to get this idea with just a couple quick examples. Let's say we have this series right here. We have series sum from n1 to infinity of this part right here is making the signs alternate. So that means we have an alternating sign, and this is the an rule over here. All right, so the first thing we're going to do is we're going to identify that this is an alternating series. Right, or state we're doing an alternating series test. Since this is an alternating series, what we have to do is just check two things. One, we have to check that the limit as n approaches infinity of the an rule is equal to 0. So that would be, in this case, the limit as n approaches infinity of n over 2 to the n minus 1. Now we have to somehow show that this is 0. Okay, so I think in this case we'll invoke the L'Hopital's idea. Limit as n approaches infinity of the numerator is infinity. Limit as n approaches infinity of the denominator 2 to the n minus 1. So if you raise 2 to an infinite number of times, that will also go to infinity. So we have an infinity over infinity, which means we can use L'Hopital's rule. So this is equal to the limit as n approaches infinity of the derivative 1. And the derivative here is the copy times the natural log of the base, because it wasn't e, times the derivative of the inside, which is 1. Right, so now this is a constant over something that's going to infinity. So that is in fact equal to 0, and that means the first requirement for the alternating series test to converge is met. The second thing is we have to show that an plus 1 is less than or equal to an. So I write it this way with a question mark. Is that true? All right, so what you can do is you can try to make a fraction. Now, this is not going to work in this case, but if I just write this rule, n plus 1 over 2 to the n plus 1 minus 1, which is just n, so n plus 1 over 2 to the n, and then assert, is that less than or equal to the original rule? In other words, I go the current term, this is the current term, and this is the next term. If it's super obvious that that's true, then you can just stop there and state, yes, that's the reason why I think it's true. But when we have n's in the numerator and the denominator, it's difficult to do it this way. So instead, we're going to use a derivative. We're going to imagine that we have a function, which is x over 2 to the x minus 1, and take the derivative of that function, kind of like with the integral test. So this would be low d high minus high d low. The derivative is a copy times natural log of 2 times the derivative of the inside, which is 1 over low squared, 2 to the x minus 1 squared. And I just want to determine the sign of this. So this is going to be 2 to the x minus 1 minus 2 times natural log of 2 times x times 2 to the x minus 1 over 2 to the x minus 1 squared, which would be, I can factor out a 2 to the x minus 1, leaving a 1 minus 2 natural log of 2 times x. And then there's 2 of these here, so there's a 2 to the x minus 1 times another 2 to the x minus 1. So those cancel. So you somehow have to convince yourself whether or not this is a positive or negative derivative. Okay, the bottom of this will be 2 raised to some power, so that will be positive. The top will be negative because this x, as once we're past 2 times natural log of 2 is going to be larger than 1, so this is negative. So this is less than 0, and therefore this is met as well. So both conditions for the alternating series test are met. So then we can finish by saying this. We can say, since, and I'm going to use this work, since that's true, the series n equals 1 to infinity of negative 1 to the n over 2 to the n minus 1 converges by the alternating series test. Okay. Or if you want, you can say, since the limit as n approaches infinity of a to the n is 0 and a to the n plus 1 is less than a to the n, the series converges. All right, so that's how it works. Real straightforward. You just identify that you have an alternating series. I know their rubrics will say this is an alternating series, and then they'll show the work. All right, let's do another example of that. So we've got this one. It's an alternating series. So you can say this is an alternating series. I'm going to do some abbreviation here. That kind of abbreviation is okay. And that means we're going to check 2 things. So the first thing is, what is the limit as n approaches infinity of the generating rule, ignoring the sign? Right? By inspection, that is 1, and therefore that is not 0, and therefore this fails the alternating series test. Right? So we cannot use the alternating series test because these are conditions for its use. So that means I'm going to have to switch to a different test. The good news is that when an alternating series test fails, it's usually because of this first criteria here. And if that is not 0, then we can use the nth term test. Remember, the nth term test for divergence just said that it doesn't matter. There's a theorem that says that if the absolute value of the series converges, then including the negative signs also converges or diverges, works either direction. And therefore, we just ignore this part when we do the a-n rule. Since the limit as n approaches infinity of n squared is 1 and is therefore not 0, you can say that this series, n equals 1 to infinity of negative 1 to the n plus 1 n squared over n squared plus 2. Hold on. You can say, therefore, negative 1 to the n plus 1 n squared over n squared plus 2 diverges by the nth term test. So the good news is when the alternating series test cannot be used, typically the nth term test will work, because if it's not used because of the first criteria, that's exactly the test that we call the nth term test. Okay, so this one diverges by the nth term test because we couldn't employ the alternating series test. Okay, let's do another example. Let's try definitely an alternating series here. That makes it so we'll identify it is an alternating series. So we're going to try first the limit as n approaches infinity of the generating rule without the sign. And let's see, that's going to be, let's use L'Hopital's. So change sign, colors there. That goes to infinity. The denominator also goes to infinity. So we have the indeterminate form infinity over infinity. We can use L'Hopital's rule. That makes this equal to the limit as n approaches infinity of the derivative, which is 1 over n, and the derivative there is 1. So that is the limit as n approaches infinity of 1 over n, which is 0. So that means the first criteria is met for the alternating series test. The second one is we have to say that an plus 1 is less than or equal to an. That's too difficult to do with like a fraction compare. But I think what we can do is we can make the function. So if the function is natural log of x, we'll take the derivative to see if the derivative is negative. Let's see, f prime of x would be low d high minus high d low, which is 1, over low squared. So that's 1 minus natural log of x over x squared. The bottom of that fraction is positive. The top will, because natural log goes like that, will become positive once we're above 1. So we can assert that that's negative, and that's why the function is decreasing, and therefore the terms are decreasing. So we can say, therefore, since, I'll write it this way, since limit, we can say this, since limit as n approaches infinity of natural log of n over n is 0, and an plus 1 is less than or equal to an, the alternating series n equals 1 to infinity, negative 1 to the n minus 1 natural log of n over n converges by the alternating series test. Okay, so that's how alternating series test works. One thing to know is that it can only be used to show convergence. So if it doesn't work, if either of these two don't apply, you have to use another test, but typically that's the nth term test because it fails because of the first one. Okay, let's see, another example, number 4. This one is not written in series form, but I can tell it's alternating series because we're going from a negative to a positive to a negative to positive and so on. And maybe we're going to have a rule for it, so I'm going to have to convert this into a series. It's going to have a term here with negative 1 to some power to make it alternating. And then this looks just to be n on top. And on the bottom, this looks to just be, let's see, 2 larger than that, right? So n over n plus 2. So we will have to write this in series form. If I want this to start at n is 1 here, I could just make this negative 1 to the n. That way it starts with the negative term and then positive. So here we go. We converted it into the series summation form. This is an alternating series. Is an alternating series. So we're going to do the test for alternating series. First one is we want to take the limit as n approaches infinity of the generating rule, ignoring the sign, but that is 1, which is not 0. So we can't use alternating series test does not apply. Right, but we can say this diverges by, we've got to be specific here, but we can say this series n equals 1 to infinity, negative 1 to the n over n plus 2 diverges by the nth term test. Right, so if it fails, we'll invoke the nth term test instead. All right, so that's alternating series test. See this quite a bit on AP exams. There's more to know about alternating series, which we'll cover later, but that's the basic test. Let's talk about this other one, which is called a telescoping series. So a telescoping series, pretty rare, but we need to be able to handle them. If you have series which, when you write out the terms, it expands so that you have always like a generating rule that has, something, some fraction minus another fraction. So when you expand the terms, each term has a number minus another number. And then the next series has a number minus another number, and another number minus the other, another number, like that. Well, at some point, if the right-hand side parts of this generating rule match the left-hand side parts, then you have a positive and negative version, and they end up canceling out, leaving just some terms at the beginning and some terms at the end. And so then you can evaluate what happens to this term as n goes to infinity and determine whether this sum converges to a number or not a number. Okay, so it's basically a special case of where we were able to actually come up with a rule for the nth partial sum. Okay, it's best to see what's going on here by example. So I have two examples here. Let's say that we want to evaluate this series right here. Now, this series doesn't look like what I said before, a fraction and another fraction. However, if this was an integral, we could do partial fraction expansion here. So this would start by doing a partial fraction expansion. Imagine that we wanted to say 1 over n times n plus 2 is equal to some currently unknown a over n plus b over n plus 2. We could do our partial fraction procedure. So that is, we get a common denominator, so we multiply this one by n plus 2 and this one by n. So we get a times n plus 2 plus b times n equals the current numerator, because now everything's over the same denominator, so I can ignore that. So you have an plus 2n plus bn equals 1, which means, I'm sorry, this is 2a, an plus 2a plus bn equals 1. So that means I have a plus b n's plus a constant, which is 2a, and currently I have 0 n's in the denominator, the original denominator, and a constant of 1. And then you match up the n's. A plus b has to equal 0, and you match up the constants. 2a has to equal 1, and you solve that little system. Here, this right here would be solved. A is 1/2, and then if a plus b has to equal 0, b must be negative 1/2. And that means that we can rewrite this series. So using this work here, we're going to say that this series is equal to this series, n equals 1 to infinity of a generating rule, which is a, so it's 1/2 over n plus negative 1/2 over n plus 2. Okay, I'm going to rewrite that another way. N equals 1 to infinity. I'm going to factor the 1/2 out of the entire thing so that I can write this as 1 over n minus 1 over n plus 2. Okay. So now, this structure right here, where we have a fraction or a term minus a term, that is going to be what we call a telescoping series. Okay, so how do we handle it? All right, what we're going to do is write out the terms of this. So I've got a half times the entire thing. I'll just keep it on the side. So what's this first term? If n is 1, this is 1 over 1 minus 1 over 3. Right? That's the first term. The next term would be 1 over 2 minus 1 over 4, right? The next term would be 1 over 3 minus 1 over 5. And then 1 over 4 minus 1 over 6. So what you do is you keep writing some terms out here until you notice some canceling going on. I can see some canceling happen. This 1/3 that's negative is exactly balanced by a 1/3 later in the series. And this 1/4 here, this negative 1/4 is balanced by that, right? And let me just do another term here just to emphasize the cancellation a little better. Let's see, the next term here would be 1/5 minus 1/7, and it would keep going from there. Right, so the negative 1/5 term is going to cancel here. And you can see at some point, right, starting here, now all these things are going to get canceled. The entire middle gets canceled out. But we'll be left with some terms at the beginning. There's 2 that happened before we got to the cancellation, which will just keep going, because this negative 1/6 is going to get canceled. This 1/7 is going to get canceled. It's going to keep getting canceled. So what's going to happen at the end of the series? At the end of the series, we're going to have a term wherever we stop. So let's say we stop at the nth term. So this term is the rule itself, 1 over n minus 1 over n plus 2. That's the last term. And then since I had 2 of these, I'm going to write another term, which is the one right before that, 1 over n minus 1 minus 1 over n plus 2, but minus 1. So that is n plus 1. So these are the last 2 terms. So what's going to happen is this is going to end up canceling something earlier, and this is going to end up canceling something earlier, and I'm going to have just those 2 terms left. So I'll have 2 terms at the beginning, 2 terms at the end. And that means that the rule for the nth partial sum is 1 over 1 plus 1/2 minus 1 over n plus 1 minus 1 over n plus 2. Remember we said that if you can come up with the rule for the nth partial sum, then you can just see what happens as you take the limit as n approaches infinity of that rule, right? Now, actually, this is all times 1/2, but let's ignore that for a sec, right? So this would be the limit as n approaches infinity of, well, we don't even have to do the limit for the first part there, right? This is Sn. So this is just 1 plus 1/2 plus whatever this limit as n approaches infinity of this rule, negative 1 over n plus 1 minus 1 over n plus 2 is. Okay, so now we evaluate that. So whether or not this series converges or diverges depends upon whether those 2 terms converge or diverge when n goes to infinity. Since this happens to be a constant over infinity, this goes to 0, that goes to 0, and therefore this converges, right? In fact, it converges specifically to the sum, this 1/2 times 1 plus 1/2. So this is another case like the geometric series where I actually have the value that it converges to, right? But with this, we can say this. Therefore, to show all this work and say, therefore, this telescoping series converges. Okay? So this is not an official test. It's basically recognizing that there's a form where the very first thing we did, where we came up with the rule for Sn, works. This is super rare, but we have to talk about it. It's part of the curriculum. It makes sense to put it in with alternating series because it involves cancellations of positives and negatives. All right, I'm going to show you one other example here to wrap this up because, yeah, these get really long. Like integral tests, you would only do this if absolutely necessary. Okay, so let's say we had this series. First, I'm going to do partial fractions to try to put it in the form of a telescoping series. So to start, if I have 4 over n times n plus 4, I'm going to say that's equal to a over n plus b over n plus 4. Okay. And then I'm going to go through my process of partial fractions, which is, this is going to be the a times the n plus 4 denominator plus the b times the m denominator, n is 4. So this is an plus 4a plus bn equals 4, which is a plus bn's plus a constant that's 4a equals 0 n's plus a constant that's 4. Right, we'll match those up. So a plus b must be 0, and those have to match. So 4a has to be 4, and then we'll solve that system. So if 4a has to be 4, a is 1, and if a plus b has to be 0, b is negative 1. So that means I get to rewrite this sum this way. N equals 1 to infinity. This is equal to a, which is 1 over n, plus negative for b, so minus 1 over n plus 4. So when we do partial fractions, this turns into a telescoping form. Telescoping series. Okay, so to solve this, there's not a test, but there's a procedure. We're going to write some terms out. So this is equal to 1 over 1. I like to put it in parentheses. 1 over 1 minus 1 over 5. Plus 1 over 2 minus 1 over 6. Plus 1 over 3 minus 1 over 7. Plus 1 over 4 minus 1 over 8. Plus 1 over 5 minus 1 over 9. Plus 1 over 6 minus 1 over 10, and we'll write more if we need. All right, then we're hoping there's cancellation. So is there any place where negative 1/5 gets canceled? Yep, way down here. Negative 1/6 gets canceled here, which means all those other ones are going to get canceled, right? But what did we leave at the beginning? 1, 2, 3, 4 terms, which means on the back end of this, we're going to have 4 terms. So let me start at the end here. The last term will be the rule, which is 1 over n minus 1 over n plus 4, and then this will be 1 less than that for n. And that's 1 over n minus 1 minus 1 over n plus 3. There'll be a term with 1 over n minus 2 minus 1 over n plus 2. And then there'll be a term which is 1 over n minus 3 and minus 3 minus 1 over n plus 1. Okay, and all of these ones will be canceled, leaving just these 4 terms on the end to match the 4 that were at the beginning, which means that the rule for the nth term is going to be 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. Let's see, minus 1 over n plus 1 minus 1 over n plus 2 minus 1 over n plus 3 minus 1 over n plus 4. So then we have to take the limit as we take this last term and move it all the way out to infinity of just this part here of that rule, and that ends up being, let's see, this is a 0. So this, well, this limit is equal to 1 plus 1/2 plus 1/3 plus 1/4. Okay, got it right in here. 1/3 plus 1/4 minus, when n goes to infinity, this becomes 0, minus 0, minus 0, minus 0. That converges. So therefore we can say, therefore this series, that converges, n equals 1 to infinity of 4 over n times n plus 4 converges. And then maybe I'll just note again, this is a telescoping series. But in this case, there's not really a test. So College Board is expecting to see some work here like this to show that you analyzed it. All right, that's it for that video. You can look in the homework and the solutions in the homework, especially in the extra packet, if you want more help and more examples.